Have you ever wondered how AI do work so well? Whether it's Meta AI, Gemini, Claude, ChatGPT. Yes, this AI can perform so well from text generation, summarization, question answering, and any kind of support that you can think of. All the chat have their different advantages and different disadvantages. However, I'm not going to cover all about that in the video, because I am here to explain a brief overview of natural language processing. How do we go from complicating our lives with feature selecting from what we are today with the GPT and all the other AI? Well, we'll first start by the feature selection in the old school way, should I say that. Next, the word embeddings. At the third time, dynamic word embeddings, and finally the transformers, the main technology behind the AI I have mentioned. And we will get started with the feature selection method. By the way, I am not going to cover all the methods, so if I am missing some, and if you want a video dedicated on the history, please let me know in the comments below. First of all, how do we extract the features from the text? Because text is a text, it's not a numbers, and I hope you don't want to speak with numbers, right? Well, if you do, let me know in the comments. I'm very curious about that. When I say talking with numbers, it means talking numbers in the real world, not just encoded or etc. I have already made a full series on the Sudoku with digital recognition, and we can see that it was quite a simple process, because an image is composed of pixels, and these pixels are numbers itself, so the features are already in the image, and we can process those features in order to extract numerical data and numerical features to be fed into a neural network to predict what image was it. However, for text, it's text, so we need to find a way to convert those texts into numbers. And the first one is bag of words. The bag of words consists of taking the word's occurrence in a sentence. For example, if we consider the following text, the cat ate the cake, we will take a full dictionary. For simplicity, I already have those here, but you can't take up to the dictionary level. And what is the next step about that? Well, how many times each word appears in a sentence? For the word the, it appears twice, so it will have number 2. For the word dog, it doesn't appear, so it will have the number 0. And every remaining word will have the number 1. And this list of numbers will be used as features for NLP task. For example, text classification. However, counting word occurrence doesn't really do much. It doesn't do the trick well, because when we speak, we don't care about how many times I have said so, the, etc. There is another feature extraction. This was mainly used for query task or information retrieval. TF-IDF. Time frequency, which is roughly almost the same as the bank of words. However, we also have the IDF, inverse document frequency. The point is, the value of a word is not only depending on its own occurrence, it also depends how rare it is according to all the text or documents. For example, let's say you are making a search which contains the words the and banana. You have 5 articles about sports or policy, well, anyway other than cooking, but one is talking about how to make a banana cake. So for the word the, it will surely appear in the banana article, the one you were looking for, but it will also appear in all the other articles, which brings its value to 0 or a very low value. Why? Because it's present everywhere, it's not really relevant. However, the banana, not only it is present a lot in the banana cake article, however, it is not present in the other, which makes the word rare and therefore relevant to your search. And that was 2 main feature selection. Well, very outdated today. And there is several more. For example, getting the category of a word, if it's a verb is a noun, a verb, an adjective, etc. We could add that for features, especially for entity recognition. However, all these outdated. Not only they don't perform very well compared to what we have today, but also they need a lot of manual work. I'll give you an example that I haven't covered in this video. Stemming and lemmatizing. Stemmatizing and lemmatizing consists of transforming text or cutting them down. For example, eat and eating. Easy, you remove the ing. However, code and coding, you have an e at the original form, so you can just take away from that. So it needs a lot of robust vocabulary. So what we don't feature is chunking down and doesn't care. That's why stemmatization is doing. However, it can lead to confusion. For example, that same word cod. If we cut the word down, no matter what, we will end up with cod, which is a fish. Okay, I love that, but this doesn't help us very much. Another manual work is step word removal, all the words that doesn't bring any relevance. For example, the. So when I have said there as an example, that was a bit wrong, because in real practice we wouldn't remove that word if we are doing those information retrieval in the social media. We can find and mine data text from there. However, social media is a great place to find completely messy words and spelling mistakes. So this is another manual task. Those problems will be solved when we will reach our level that we are today. But we will move to the next section, word embedding. They consist of taking a word and pulling into one vector, which means a text will be two-dimensional data. However, what size of length can we do, and what are the values of the vector? Honestly, no, I have no idea. Well, yes, I have an idea, but I don't know what precisely it is. For example, the size of the vector, that only depends, it's up to you. You can build 100, you can be 50 for small. More advanced models will use a few thousands of size. But now, what value it is? And that's a very good question. They are not built randomly. Well, they were initially, because we are training them, they build relationship between them. I'll give you an example with capital and country relation. If you take the vector of the word France and you take away the vector of Paris and you add up the vector of Madrid, you will end up with Spain. And this is not the only relationship. I'll give you one more. If you take king, you take away kingdom, and you add up empire, you will end up with emperor. So it has many of these relationships. I'm not going to cover them all. Now we'll move to the next section, dynamic word embeddings. Now we have seen the word embeddings, and they are really useful and they can improve the accuracy of the NLP task. However, how can we add some dynamism inside the vectors? A word will give you the same vector for the same words. So you might say, yes, but that's what we want. Identify the word so we can use it. Well, not really. Two examples will show you that. I ate an apple pie and I bought an Apple Watch. Both sentences have the word apple. They will give us the same static embedding. However, as a human being, I know that this is definitely not the same apple. The first one is obviously the fruit, and the second one is obviously the technology brand. And how is a computer supposed to know that? With dynamic word embeddings, yes, it pays attention to the context. In the background, they use static word embeddings. However, depending on the context to the other words surrounding the apple, it will change itself so that it will be more adaptable to the context. So static word embeddings, they capture relation well with the trained words. However, they don't capture the context. But dynamic word embeddings does. And this is where we get to transformers encoder. The transformers encoder's goal is basically this. We'll first go through the main architecture. This is from the paper called Attention is All You Need, because it pays attention to the context. It looks a bit scary, but we'll skip the details of the encoders for now. So now, yes, we'll change that. First, we have the word embeddings. This could be static word embeddings, and we can use a pre-trained, like Botuvec or Glove, which are able to find the relationship we talk about the static word embedding. The next step is to add positional embedding. This is according to the position, we will add some extra value so we know for a certain position. The encoder, as I said earlier, is like a dynamical word embedding. And then we have the decoder. The decoder is similar. It encodes the outputs and use the encoded inputs to have new numerical data to predict what next word should be. And yes, this is the main key thing you need to remember as a transformer. It takes an input, an output, and predicts the next word. You want an example? Great, I have a great one. If we are translating the English sentence to Italian, I like pizza, mi cuci la pizza. If you're an Italian speaker, please forgive me. Let's suppose we have a transformer that has been trained to translate. We'll encode the English sentence, I like pizza, and we'll predict the next word according to the encoded outputs. But hold on, we don't have an output yet. We haven't translated anything. Well, yes, because we will add a special token, the start token. We can add that at the input, but we also need that at the output. This is the output basically, the start token. Once we have the start token, we can proceed. So if the transformer has been trained well, it will predict mi, Gucci, la, pizza. So pay attention to this. It generates one token at a time. However, we have done translating, but how does the computer know that? It could be generating other tokens forever. But we can solve that. Two ways. One way is to add a limit. Even ChatGPT has a limitation on the generated token. Sometimes it cuts off the response and we can just ask to regenerate later. However, there is another way. And technically, both of the methods could be used. The second method is the end token. Yes, this is another special token. We need to add the end token at the input so that we can predict the end token at the output. And we can simply say, okay, as long as we have predicted the end token, that's it, we have done our job. And this is the case, we have done so. We have translated the English sentence to Italian. Right, that was the full architecture of the transformer. There is also two types, but don't worry, if you have understood the basic idea of the two other ones will be straightforward. Firstly, the encoder only consists of using the features of the dynamic embeddings, and you can use it, for example, text classification or sentiment analysis, sentiment review, etc, etc. But the decoder is actually very interesting. Decoder only consists of having an input text and consider it as an output so that we can just generate. So this is really it. We don't sometimes need the encoder bit. We can just have any sample text and generating until we have reached the limit or have arrived at the end token. And why I'm saying that this is one of the most interesting architecture, this is the same architecture behind ChatGPT, or should I say GPT. Yes, because GPT has once existed in 2018, which is 4 years before ChatGPT was released. It was almost a failure, it has been rejected multiple times. Then after that, they released GPT-2, which performed slightly better. However, for GPT-3, 3.3 and above, are just completely game changer. They have implemented better way to manage their data. How do we generate data? How to filter those data? There has been many steps so that they can fit a very reliable model. And also, it is very costly. Can you imagine yourself having to generate data with a question? So imagine that the question is the output and the rest of the text is the right answer. Do you know how many you need so that you can base on the general model? Well, they have invested billions and billions to perform this operation. Alright, looks like we have wrapped up this section, the transformers. So I hope you have been able to see how we went from bag of words to transformers to what we are using today. And this is only the starting. Yes, we are still starting the point. I have made a brief overview. However, we don't stop here. We want to use that benefit of transformers. And also, this is only natural language processing. I haven't talked about how images are fit into transformers. So don't forget to subscribe. Activate the bell of notifications and you don't miss any tutorials and transformers. If you are curious about how to implement digital recognition, I recommend watching this video where I implement digit recognition with neural network, but you can also apply to almost any images you want. Otherwise, keep coding and I will see you in the next video.